All right, I would like for you guys to copy this into page 11. This is different than yesterday's because I combined 5th and 6th periods data together. So please go ahead and copy that onto page 11. All right. I'm going to come right back here, but I want to begin looking at the questions. I'll let you get that copy down real quick. So between yesterday, 5th and 6th period, we had 33 students total present. Of those, 17 of them could taco tongue. 3 could not do either. 4 people could evil eyebrow but couldn't taco tongue, and 9 people could taco tongue but couldn't evil eyebrow. So what I want to look at now, here in question number 2, given that the person selected is a yes evil eyebrow, this right here is called a condition. That is called a condition. Once I have a condition, I'm no longer looking at the grand total. I'm not looking at everybody involved anymore. When I say given that the person selected is a yes evil eyebrow, I am only looking at this much of the table. I am totally and completely ignoring this for part A. So what is the probability that somebody can yes evil eyebrow if they are a yes, or sorry, what's the probability they can taco tongue if they're a yes evil eyebrow? 17 out of 21, yes. 17 out of 21. So the other thing I want to talk about is notation here. How do we write proper notation for this? So I'm going to start with my big capital P in parentheses for probability. This piece here, the condition, that's not what I want the probability of. This is a known thing. I'm narrowing it down to just these people. The probability is that they are a yes taco tongue. So the first thing inside the parentheses is what I want to find the probability of. So probability, capital P, parentheses, yes taco tongue. And then I put my condition. We have this vertical line that we read as given that. And then after that line, we put whatever our condition is. And as we mentioned, that is 17 out of 21. My numerator is the intersection of yes taco tongue and yes evil eyebrow. My denominator, however, is only the total of my condition. This is the total of just the yes evil eyebrows. Does anybody happen to know what 17 over 21 is as a decimal? Or could you find it? Grab a calculator for me real quick. Calculate that for me.
It's like 0.8095.
Yes. 0.8095, or about 80.95%. I want you guys to do part B. Use part A as a model, but I want you to do part B. Notation, fraction, decimal, and percent. I'm only going to give like 45 seconds to a minute. Do part B, notation, fraction, decimal, and percent.
says yes and then two E's.
The EE means evil eyebrow.
Oh.
Evil eyebrow. TT is taco tongue. I just didn't have enough room to write that whole thing out.
Okay.
All right. So notation should look like this. You do not have to have what I wrote in pink. You do need to know how it's read, and you do need to know which part of the statement is your condition, because that affects your denominator. What would this be as a fraction? 9 over 12, which comes out to be what percent? 75%. These are both called conditional probabilities because they have a condition. Based on these two previous answers, part A and part B, what conclusion can we make about taco tongue and evil eyebrow? I like what you're saying, except according to these two, I don't even know what the probability is that somebody can just yes taco tongue. I'm not disagreeing with you. I just don't have all of that information to be able to make that statement. But I do like where you were going with that. You said based on the probabilities, it's what?
It's more likely that someone that will select someone who can taco tongue and evil eyebrow than someone who can taco tongue but they can't evil eyebrow.
There, that one. It's a higher probability that if they can evil eyebrow, then they can also taco tongue. If they can't evil eyebrow, it's a lower probability that they can taco tongue. So what I would say is people who can evil eyebrow are more likely to be able to taco tongue than those who can't evil eyebrow. Is it a huge difference? No, but there is a difference. There is a difference. All right, let's go look at number 3. But before we answer number 3, we have this definition here. Two events are independent if knowing whether or not one event has occurred does not change the probability that the other event will occur. Two events are independent if knowing whether or not one event has occurred does not change the probability that the other event will occur. So let me give you an example of things that are independent. The probability that you get an A on the next test, and the probability of whether or not I oversleep tomorrow. Those two are completely unrelated. If I oversleep tomorrow, that does not affect your probability of getting an A on the next test. If I don't oversleep tomorrow, that does not change the probability of whether or not you get an A on the next test. Does that make sense? So knowing whether or not I oversleep tomorrow, you're not all of a sudden going to go, yes, I've got a better chance of getting an A now. Are the events, yes, taco tongue, and yes, evil eyebrow, independent? No. Knowing whether or not a person can evil eyebrow does change the probability that they can taco tongue. The percents are different. If the percents were the same, then I would say that they are independent.
This is also I'm going to, yes, this is a small sample size.
Mm-hmm.
So with this sample size, no, they are not independent. with a larger sample size, it's entirely possible that the evidence could show they are independent.
It is possible. It is possible. However, I will tell you, after doing this for 4 years, it has turned out this way every single time. So my sample size has gotten bigger and bigger and bigger as years have gone on. And every single time I have found that these percentages are different. So chances are we would continue to find that they're not independent. Yes?
Can you only, when you're trying to process if it's given, do you have to use a given?
Yes. Yes. There is another way of showing that two events are independent, but it's all built on or based on a given. All right. I would like for us to turn the page. We're going to go over to page 12. If you look up at the top of page 12, I have a two-way table here with my incredibly realistic data for all the seniors at Pike. By the way, there's only 600 seniors at Pike. I know. I made these numbers up because I want to demonstrate something, so I made the numbers up. I want you guys to find the 3 probabilities that they are describing here in parts A, B, and C, and then I want you to answer question D. I'm only going to give about 2 minutes for you to find these probabilities. Please change them into decimals. Don't just leave them as fractions so that you can compare them. You doing okay? All right. I'm only going to give about 2 minutes. Oh, you're changing. Never mind. You're doing the calculator. It looked like you were just like bopping to something. It's like, that's fine when you're done. Write them down as fractions first, then change them into decimals so that you can compare them. Yes.
Which one goes first? Like, which one is the condition every time?
That sounds good. Flip it over. Let's look at the other side so that we can like compare to this. That is your condition.
So it's the first one.
The first one is the probability of. So what's the chance of this if I know this already?
Because the line means given that, so would it be yes, taco time given that it's under, like, it's out of yes, evil eyebrow?
Yes. Yep. One of the things I want to mention is that when you are given problems in word form, a lot of times they will use the words given that. Sometimes they won't. Sometimes it's an implied given that. They might say if this instead of given that this. Same thing. It's still your condition. What is the probability of yes taco tongue? 480 as 600. What is that as a decimal? 80% or 0.80. What is the probability of yes taco tongue given that yes evil eyebrow? 180 over 200, which comes out to be what percent? 0.9 or 90%. What is the probability of yes taco tongue given that no evil eyebrow? 300 out of 400, which comes out to be 75%. Are yes taco tongue and yes evil eyebrow independent? No. What would these look like if they were independent? They'd all be the same. That's what we're looking at on number 5 now. Yes taco tongue would be 80%. Yes taco tongue given yes evil eyebrow would also be 80%. Yes taco tongue given no evil eyebrow would also be 80%. I'm going to call this one up here event A, because I want to be able to write this symbolically now. I'm going to say that this is the probability of A given B. And this one right here has the no for my condition. So A given B complement. If the probability of A is exactly the same as the probability of A given B, is exactly the same as the probability of A given B complement, then the events are independent. You do not have to find all three probabilities. Just comparing two of them would be fine. If these two are the same, these two will automatically be the same. If these two are the same, that one will be the same. So I want to know what this table would look like if things really were independent. I know that 480 out of 600 is 80%. That's my 80% yes taco tongue. If I wanted yes taco tongue, given that yes evil eyebrow comes out to 80%, what should go right here? 160. Why? Yep. That is 80% of my total in my yes evil eyebrow. So what would this be? 40. What should go here? 320. Because 320 is 80% of the total for no evil eyebrow. 320 is 80% of 400. So then what goes down here? 80. If I want to know if two events are independent, I can calculate this probability right here and compare it to this conditional probability and compare that to this conditional probability. If this is the same as this, is the same as this, then my events are independent. If they come out to be different, even slightly different, then they are not independent. So that's what we're going to write down for number 7. Check if the conditional probability of one event stays the same given whether or not the other event occurs. And then there's some room down at the bottom of the page. I wrote really big on the screen because I had a lot of room. You do not need to write this big, but it is important. If two events are independent, and I know we wrote this down earlier, but I really want you to write it down again. If two events are independent, then the probability of A is equal to the probability of A given B is equal to the probability of A given B complement. The probability of event A does not change when event B does or does not happen. I would. right. Getting ready to scoot on to the next page. I'm going to go over to page 13 now. You good, Jade? Okay. I just didn't want to go too fast if you still needed to look up at the screen. Conditional probability. And this one is huge. This one is huge. The probability of one event given another event has occurred. Please circle this. This is the formula that you will need to use if you have not been given a two-way table. If you can't look at the two-way table and just narrow it down to one column or one row, if they give it to you in words, you need the probability of both events, my intersection, up on top. On bottom, this is only the probability of the condition. So we have the intersection up on top, and only the probability of the condition, the thing that we know, goes on the bottom. And I'm not going to spend any more time talking about this over here because we've written it down several times and you've got it written down again. So I want to move right on to the check your understanding. Take about 3 minutes to try to answer those 3 questions to the best of your ability. Take about 3 minutes to answer those 3 questions, and then we will go over them together. Has everybody had a chance to pick up the new homework? New homework, by the way, is due on Tuesday. New homework is due on Tuesday. You're welcome. That's okay. You're welcome. Anybody else need a copy of the new homework? Does everybody have a copy of the new homework? All right. Wonderful, wonderful. All right, we're only a couple minutes from the bell, so let's go ahead and go through this. The probability of C given that S is 40 out of 100, or 0.40. Interpreting that in context, taking this notation right here and turning it back into English. Given that the mother was surveyed in 1976, that's my condition, that's the first thing I'm going to mention, there is a 0.4 or 40% probability that she had 4 or more children.
A mother surveyed in 1976 had a 40% probability of having 4 or more children.
Yes. Yes. All right, number 2. Given that the mother chosen was not surveyed in 1976, what's the probability that she has 4 or more children? 13%. Because we're looking specifically at the other 2 years that surveys were done, which are mutually exclusive, so we can add things together, and we don't have to worry about subtracting out an overlap, because there is no overlap between these years. Are the events surveyed in 1976 and 4 or more children independent? No. Mothers surveyed in 1976 are more likely to have 4 or more children than mothers surveyed not in 1976. The probability of C given S is not the same as the probability of C given S complement.
Should you just write it like the second one?
Could you just write it like the second one? Yeah. Yeah, as far as your explain, you could write that down. Now, on the AP exam, I'd probably have a little bit more. I'd probably have some words to go along with that. Unless you have, like, if you've clearly defined your variables elsewhere, then you should be okay with just that notation.
Okay.